Hi, this is your video for sections 5.1 and 5.2, and in this whole chapter we're going to be talking about probability. So section 5.1 is probability basics. The objectives in this section are 1. Define basic terms and notation. 2. Present 3 different approaches to finding probabilities. And 3. Define complementary events. So objective 1 is to define basic terms and notation for probabilities. In considering probability, we deal with procedures such as taking a polygraph test, rolling a die, answering a multiple choice test question, or undergoing a test for drug use that produce outcomes. An event is any collection of outcomes or results of a procedure. A simple event is an outcome or an event that cannot be further broken down into simpler components. And the sample space for a procedure consists of all possible simple events. In other words, the sample space consists of all outcomes that can't be broken down any further. Here's some examples of some of those probability terms. So here's a procedure, rolling a die. The sample space would be all of the possible simple events that are outcomes of the procedure rolling a die. So the possible outcomes when we roll a die are 1, 2, 3, 4, 5, and 6, depending on which of those faces come up. Another procedure would be answering a multiple choice test question. So to find the sample space for that procedure, we'd think about the different possible answers for the question. So these would be something like A, B, C, and D. Another procedure would be undergoing a drug test. And the possibilities for the outcomes of the drug test would be either that it's positive or it's negative. So that would be our sample space. Another procedure would be to look at the births of 3 children. And the sample space in this one is a little bit more complicated because we're actually looking at the genders of the 3 children. And in fact, we're even including what order the genders happened in. So our sample space would be these 8 possibilities. Either we had 3 female children, or we had a female, and then a male, or female, male, female, and so on. So we've got a total of 8 possibilities as events in our sample space. Now, in that last procedure, the event of 2 females and 1 male is not a simple event because that could happen in 3 different orders. So it could be broken down into 3 simpler events. So either the 2 females came first and the male came last, or the male was in the middle, or the male was first. So there are 3 different possible ways that we could get 2 female children and 1 male child. Now the outcome female, female, male is a simple event because it can't be broken down any further. Now the notation for probabilities, a capital P denotes a probability. We usually use capital letters to denote specific events, like A, B, and C. And P of A denotes the probability of event A occurring. Objective 2 is to present 3 different approaches to finding probabilities. So approach number 1 is the empirical approach, or we can call it relative frequency approximation. So in this approach, we conduct or observe a procedure and count the number of times that event A actually occurs. Based on these actual results, the probability of A is approximated by looking at the number of times event A actually occurred and dividing that by the number of times the procedure was repeated. This is why it's also called the relative frequency approximation approach, because what we're finding is the relative frequency of event A. Approach number 2 is called the classical approach. In this one, we assume that a procedure has n different simple events and that each of those simple events has an equal chance of occurring. This is a requirement if we're going to use the classical approach, is that we have to be able to break our procedure down into outcomes that each have an equal chance of happening. So in this situation, if event A can occur in S of these n ways, then our probability is S over n, or in other words, the number of ways that A can occur divided by the number of different simple events in our sample space. Again, if we're going to use this approach, we have to make sure that the outcomes are all equally likely in our sample space. The third approach is subjective probabilities. In this one, the probability of event A is estimated by using knowledge of the relevant circumstances. So the question is, which approach should we use in a specific situation? Again, the classical approach requires equally likely outcomes. If the outcomes aren't equally likely, or if we don't know anything about the likelihood of different possible outcomes, then we can't use this approach. If we have data, in other words, results from many repeats of a procedure, then we can use the empirical approach to approximate probabilities. And if we have enough knowledge of the circumstances to make an educated guess, we can develop a subjective estimate of the probabilities. Here's some examples. First, find the probability that a randomly selected car in the United States will be in a crash this year. Well, in order to do this, we would need some kind of data. So for a recent year, there were 6,511,100 cars that crashed among the 135,670,000 registered in the United States. This is based on actual data from the Statistical Abstract of the United States. So using this data, we can use the empirical approach. The probability that a randomly selected car will be in a crash this year would be the number of cars that crashed from our data divided by the total number of cars registered. So that would be our 6 million and some divided by our 135 million. And this gives us a value of 0.0480. Now in this one we couldn't use the classical approach since our two outcomes, and that is that the car crashes or that it doesn't crash, are not equally likely. Really the only thing that we have is data, and so there's no way that we can do anything with equally likely outcomes in this one. Here's another example. Find the probability that in 3 coin flips you get exactly 2 heads. In this one we can use the classical approach because we can assume that the coin is fair, so there's a 50% chance that in any one flip that you'll get a head, and there's a 50% chance that you'll get a tail. Since we're doing 3 coin flips, we actually end up with 8 simple events in our sample space. This is a lot like the example we looked at earlier with the 3 children and them being male or female. So the 8 possibilities in the 3 coin flips are either that we get all heads, that we get head, head, and then a tail, or that we get head, tail, head, and so on. So these are all 8 of our possibilities. We can assume that each of these outcomes is equally likely. And we're looking for the probability that we get exactly 2 heads out of our 3 flips. So if we look at our events in our sample space, the ones that have 2 heads are head, head, tail, head, and tail, head, head. So that tells us there are 3 ways out of the 8 in our sample space that our event can occur. That means our probability would be 3 divided by 8, or 0.375. Again, in this one, all we're doing is figuring out how many ways our event can occur, and assuming that each event in the sample space is equally likely, we divide by the number of events in the sample space, and that gives us our classical probability. One more example. A survey asked this question about Kentucky Fried Chicken. Will KFC gain or lose business after eliminating trans fats? Among the responses received, 1,941 said that KFC would gain business, 1,260 said that KFC business would remain the same, and 204 said that KFC would lose business. Find the probability that a randomly selected response states that KFC would gain business. So first, it'd help if we had a little bit of summary of this information. So we had this many responded gain, this many responded the business remains the same, and 204 responded that there was a loss. The total responses were 3,405. Since we have this data, we can use the empirical approach to find our probability. So the probability that a randomly selected response says the business will gain would be the number out of all the responses that said there would be a gain in business out of the total number of responses. So that would be 1,941 divided by 3,405, which is 0.570. Another example, find the probability that the next president of the United States is from Alaska. So in this one, our sample space consists of two possible outcomes. Either the next president is from Alaska or not. We can't use the empirical approach in this one because there has never been a president from Alaska. We can't use the classical approach because our two possible outcomes are not equally likely. So the only one left is to find a subjective probability. So we can make a subjective estimate based on the population of Alaska compared to the rest of the country. The population of Alaska is 0.2% or 0.002 of the total United States population. So if we're just going off of that, we could say that the probability of selecting a president from Alaska might be 0.002. But if we consider the remoteness of Alaska and the fact that that presents special challenges to politicians from that state, we would probably say that the probability would be even smaller than 0.002. So we could maybe estimate the probability as 0.001 or 0.1%. So this is using some information that we could get plus some other knowledge that we have to make a subjective estimate of the probability. Here's another example. Find the probability of winning the grand prize in a lottery, where each ticket has 5 numbers between 1 and 20. Now, since each combination of numbers would be equally likely, we can use the classical approach in this one. The number of possible outcomes, or different combinations of 5 numbers, is 15,504, and we'll learn how to calculate this number later in Chapter 5. The probability of any one combination of the 5 numbers being chosen is 1 out of 15,504. So out of all those different combinations, if we're going to choose 1 out of all of those, then the probability of choosing that one is just 1 divided by our total number of possibilities. If we divide this, we get 0.00006. So the probability of winning the grand prize in this lottery would be 0.00006. Now let's look at the empirical approach and what it has to do with the law of large numbers. When we're using the empirical approach, we obtain an approximation instead of an actual value. And as the number of observations or the number of repeats of our procedure increases, the approximations tend to get closer to the actual probability. In other words, if we could calculate the classical probability, then the empirical probability would get closer to it as we ran more and more repeats of our procedure. And this is called the law of large numbers. So as a procedure is repeated again and again, the empirical or the relative frequency probability tends to approach the actual or the classical probability. Here's an example. In the game of solitaire, the outcomes, or the hands dealt, are all equally likely, but the procedure is so complicated that calculating the probability of winning using the classical approach would be extremely difficult. So in this case, it's much easier to get estimates of the probabilities using the empirical approach. The approximations will be closer to the actual probabilities the more times the procedure is repeated. We can use a computer simulation of the game to get a large number of results, and the results can then be used to approximate the probability of winning. This would be much easier than performing all the complex calculations required with the classical approach. Here's another example. If we're rolling a die, the classical probability of each of the 6 possible outcomes is 1/6, or 0.1667 if we rounded to 4 decimal places. As we keep repeating the procedure, the relative frequencies of the outcomes, or the empirical probabilities, should get closer to our classical probabilities. So here are some results. If somebody actually went out and did this, here's an example of what they might have come up with. So for each of the 6 outcomes, we have the frequency listed, how many times that particular number came up on the die. And then we have our relative frequencies here. And notice that some of them are fairly close to our classical probability of 0.1667, but some of them aren't that close. For example, the 2 came up more times than we probably would have expected, so the relative frequency here is 0.22. But again, this was only 50 trials. That's not really very many repeats of our procedure. So if we do this again, when we do a lot more trials, say if we do 2,000 trials, so 2,000 rolls of the dice, record all of the results, then notice what happens to our relative frequencies. We still have some that aren't quite as close to the 0.1667, but they're much closer than they were when we only had 50 trials. So again, as we repeat the procedure, so if we kept repeating this and got up to 10,000 trials or 50,000 trials, the law of large numbers tells us that these relative frequencies would get closer and closer to our classical probability of 0.1667. Let's talk a little bit about possible values for probabilities. Again, a probability is a measure of the likelihood of an event occurring. So we've got a range of possibilities for our probability values. Starting at the bottom, if our event is impossible, or it's something that can't happen, then the probability is 0. On the other end, the probability of an event that is certain to occur, or that has already occurred, is 1, or 100%, if we want to put it in percentage terms. And then we have all these possibilities in between. If the event is unlikely, we would have it down here with a small probability. If it's likely, we would have it up here closer to the 100%. One value that a probability can't have is a negative value. So we can't have any probabilities that are less than 0. We also can't have probabilities that are greater than 1 or greater than 100%. In this class, we'll define an unusual event as one that has a small probability of occurring. And in this class, for the most part, we'll use 5% or 0.05 for our borderline for unusual events. So if the probability is less than 5%, we'll say it's an unusual event. Here's some examples of basic probabilities, and these are ones that we might hear about or see a lot. For example, there's a 70% chance of rain today. The probability of getting tails when you flip a coin is 1/2 or 50%, assuming that the coin is fair. The probability of Thanksgiving Day falling on a Wednesday next year is 0. The probability of Thanksgiving Day falling on a Thursday next year is 1 or 100%. And the probability of winning the grand prize in the lottery is very small. It was 0.00006 in the example we already looked at. This would definitely be considered an unusual event. Objective 3 in this section was to define complementary events. So the complement of an event A, which in this textbook is denoted by A with the superscript C, consists of all outcomes in which the event A does not occur. So the complement of A includes all outcomes in the sample space that are not outcomes in event A, which means that A and A complement together make up the whole sample space. Sometimes this is easier to look at in a picture. So if we have our whole sample space represented by the box, and then event A represented by everything that's in the circle, A complement would be everything in the box that's outside of the circle. So if we put A and A complement together, that gives us the whole sample space. But A and A complement don't have any overlap. There's nothing that can be in both of those. Here's an example of complementary events. A typical question on an SAT test requires the test taker to select one of 5 possible choices, A, B, C, D, or E. Because only one answer is correct, if you make a random guess, your probability of being correct is 1/5 or 0.2. Find the probability of making a random guess and not being correct. In other words, being incorrect. We already said that exactly one of the 5 choices is correct. That means 4 of the choices are not correct. The event of not being correct is the complement of the event of being correct. So we've got correct, and the complement of that is incorrect. So the probability of the complement of correct is the same as the probability of being incorrect. And since 4 of the 5 choices are incorrect choices, then the probability of being incorrect is 4/5 or 0.8. Now, if you've ever heard about multiple choice test strategies, one of these is to eliminate some choices that are obviously wrong, because this increases your probability of guessing the correct answer if you have to guess. Because if there are only 2 choices, the probability of guessing the correct one is 1/2 or 0.5. So the probability of being correct in that case is 1/2. The probability of being incorrect is 1/2. So this increases your chances of being correct, and it decreases your chances of being incorrect. Section 5.2 is about the addition rule and the complement rule. The objectives in this section are: 1. Use the addition rule. 2. Use the complement rule. So objective 1 is to use the addition rule. Here are some key concepts for the addition rule. The addition rule gives us a way to find probabilities such as the probability of A or B. When we say A or B, this is a compound event. It's any event that combines 2 or more simple events. The compound event A or B is the event that A occurs or B occurs, or that they both occur. The probability of A or B is the probability in a single trial event A occurs or event B occurs, or they both occur. To find this probability, we first need to find the total of number of ways that A can occur and the total number of ways that B can occur without counting any outcomes more than once. Here's an example. 1,000 survey responses are collected. The results are, as you see in this table. So we have gender, and then we have 3 different age groups. So if one person is randomly selected from the 1,000 survey respondents, find the probability of selecting someone who is male or over 65. So to do this, we need to find the total number of respondents that were male or over 65 without counting any of them twice. One way we can do this is to mark the cells for respondents who were male or over 65 and then just add the numbers in those cells. So if we look at all the cells for the male row, we've got 123, 275, and 113. Now we also need to count the respondents who are over 65. We already counted the 113 in this cell, so we don't want to add that one in again because we don't want to count anyone twice. So we're going to add on the 202 that were over 65 but female. So we're just adding the numbers from these 4 cells together, and that gives us 733. The other way we can do this is to add the total of the male row, so the 531, and we can add that to the total of the over 65 column, which is the 315. Now when we did that, we actually counted the ones in the intersection of that row and column twice. So these 113 people here got counted twice. So we have to subtract that 113 out so that it only gets counted once. So if we add those two totals together and then subtract the 113, we also get 733, which matches what we got doing it the other way. So either way we do it, we find that there are 733 responses out of these that were male or over 65. So the probability of selecting someone who's male or over 65 would be 733 divided by the 1,000 total responses, and that would give us 0.733, or 73.3%. So for the addition rule, we can think about it 2 different ways. The intuitive way to look at it is that to find the probability of A or B, we find the sum of the number of ways event A can occur and the number of ways event B can occur, adding them in such a way that every outcome is counted only once. The probability of A or B is equal to that sum divided by the total number of outcomes in the sample space. So that's the intuitive way to think about it. The formal addition rule says that the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. So this again is subtracting out the ones that would have got counted twice if we added the probability of A and the probability of B together. Now let's talk about disjoint events. Events A and B are disjoint or mutually exclusive if they cannot occur at the same time. That is, they have no outcomes in common. They don't overlap at all. So here's a picture of 2 events that do have an overlap. Notice we've got two circles here. We've got an overlap in the middle. So these two events are not disjoint. These two events are disjoint because they don't have any overlap. So in a situation where we have disjoint events, to find probabilities, we can just add the two probabilities together if we want the probability of A or B. If we have an overlap between the two events, then we can still add the two probabilities together, but again, the part in the overlap gets counted twice when we do that, so we have to subtract that value out in order for the overlap to only get counted once. Okay, let's go back to our example with the survey responses. Now, if one person is randomly selected from the 1,000 survey respondents, find the probability of selecting someone who is under 18 or over 65. So again, we need to find the total number of respondents that were under 18 or over 65 without counting any of them twice. So let's say that event A is selecting someone who's under 18, and event B is selecting someone who is over 65. In this case, A and B can't occur at the same time because no one can be both under 18 and over 65. So there's no overlap, and these are disjoint events. So to find the probability of A or B, we can just add the totals for the under 18 and the over 65. Since they're disjoint, we won't be counting anything twice. So we could just take the total of the under 18 column and the over 65 column and add those two together. That gives us a total of 487 responses. So our probability is 487 divided by 1,000, or 0.487. Objective 2 in this section is to use the complement rule. And we already talked about complements a little bit in the last section. So remember that the complement of event A consists of all the outcomes in which event A does not occur. Events A and A complement are disjoint because it's impossible for them to occur at the same time. And A and A complement together make up our whole sample space. So the probability of either A or A complement occurring is 1. Now if we apply the addition rule to this, we get the probability of A or A complement is the probability of A plus the probability of A complement, and we just said that those two together have to add up to 1. So our complement rule says that the probability of A plus the probability of A complement is equal to 1, and usually to use this rule we turn it around. So if we solve this for the probability of A complement, we get 1 minus the probability of A. If we solve it for the probability of A, we get 1 minus the probability of A complement. So the first one is the formal complement rule. These two other ones are how we usually use the complement rule. Here's an example. Many individuals aged 65 and older rely heavily on prescription drugs. For this group, 82% take prescription drugs regularly. What is the probability that a randomly selected individual aged 65 or older does not take prescription drugs regularly? So the word not is a good clue that you're talking about a complement. Up here we had 82% that do take prescription drugs regularly. Now we're asking about the probability that someone does not do that. So that would be a complement. So if we let A be the event that a randomly selected person over 65 does take prescription drugs regularly, then A complement is the event that the individual selected does not take prescription drugs regularly. Now, we were told that 82% do take prescription drugs regularly, so we can assume that the probability of selecting an individual in that group would be 82% or 0.82. So the probability of the complement would just be 1 minus that, so 1 minus 0.82 would be 0.18 or 18%. Here's another example. Consider the procedure of rolling a die. Let event A consist of rolling a 5. Find the probability of event A and its complement. So event A includes only one outcome, and that is that we roll a 5. A complement is the event of not rolling a 5. Since the sample space would be all the numbers from 1 up to 6, a complement, if we look at it as a set, would be 1, 2, 3, 4, and 6, just leaving out the 5. The probability of event A, where we do roll the 5, would be 1/6, because that's one simple event out of our sample space of 6 events. The probability of A complement would be 5/6. Notice this set had 5 elements in it out of the 6. And 5/6 is the same as 1 minus 1/6. So we could get the probability of this complement either by calculating it directly or by subtracting the probability of A from 1. We get the same answer either way. Now let's look at part B of this problem. Let event B consist of rolling a 2 or less. Find the probability of event B and its complement. B includes 2 outcomes, so B is the set 1, 2. So B complement is the rest of the outcomes in our sample space, so it's 3, 4, 5, or 6. The probability of B would be 2 over 6 because there were 2 elements in this set and 6 total. We could reduce that to 1/3. And the probability of B complement we could calculate by taking 1 minus the probability of B, which would be 1 minus 1/3 or 2/3. We could also calculate it directly by looking at how many elements are in B complement. There are 4, so we would have 4 divided by 6, which would also reduce to 2/3. Here's one more example. If one person is randomly selected from our 1,000 survey respondents, find the probability of selecting someone who is not over 65. So again, the word not usually signals a complement. So if we let event A be selecting someone over 65, then selecting someone not over 65 would be the complement of A. We can find the probability of event A by taking the number of respondents over 65 and dividing by the total number of respondents. So we have a total of 315 that are over 65. If we divide that by 1,000, we get 0.315. So then we can use our complement rule to find the probability of A complement, and that says we just have to take 1 minus the probability of A, so that would be 1 minus 315 over 1,000, which would give us 0.685.